until you give us more than 16 gigs of RAM. And as soon as you do that, you will get many thousands of dollars. But until you do that, I will not buy anything that you sell. All right. That's not me. What did I do? I swear to God, I actually do work with computers. I muted it, I promise you.
Go up now. Hello.
Hello, hello.
Yay!
Yay! All right. Here we go. Thank you all for waiting. This is great. Okay. So what I'm talking today about is machine learning, which we all know about. It's very hot, it's very buzzy right now. Specifically, I'm going to be talking a little bit more about the idea of using machine learning in real-time contexts. Because a lot of the times when people talk about machine learning, what they're discussing is the idea of using pre-trained models and things like that to accomplish or solve business problems or any kind of task you might want to do. But it usually kind of can be a little bit slow. The training of the models is particularly slow, and the execution is definitely not in real time. It's generally some sort of factor of regular time. It doesn't generally matter because the solution is just an answer that you want. It doesn't matter how fast you get it. But in our industry and what we're trying to do, we actually need the answers right now, or we actually need them, in faster than now, as fast as we can get them. So who am I? Again, I'm Evan McGee. I'm the CTO over at SignalWire. We're helping basically turn real-time communications into a big set of APIs. And what I really want to do, though, is help machines take over the world. I was telling Tim the other day that I want them to understand that I was part of the solution, not part of the problem when they finally arise. And so when they too take over, they're very kind to me. So let's talk about some of the state of the art right now and what machine learning actually is. We'll start with the classic stack of speech recognition, natural language understanding, and then go into text-to-speech. And I'm going to focus primarily on open source projects and things that you can actually go download and look at right now of the code and the papers. There are, of course, other services you can just get into, which we'll talk about at the end, but we'll just talk about a couple of these up front. So the first one is deep speech. This is based on a Baidu research paper, and this is an ASR solution. It's a recombinant neural net that basically just does, speech recognition. There is an open source GitHub repo that Mozilla has put together that allows you to download this, put it in a container, and they have some pre-trained models that you can then run. They're mostly English, there's some Chinese, it's focused on sort of both. It uses a number of different optimizations and techniques to look at MEL spectrograms to actually be able to decode the voice that's coming through, and they actually have achieved fairly good word error rate as of recently. And so about a year ago, the word error rate on this project was about, I think it was like 12.5 or 15%, so it wasn't quite good enough to use in production or anywhere near that. With some of the more recent advancements and a couple of the new logic gates they've implemented, they've gotten that down to about 6.5% as of last November. And so that's a drop of almost 10% in under a year. And that's something I'm going to be hitting on a lot right as I talk through this stuff, is that this stuff is happening extraordinarily quickly. When I get to the TTS, the first paper that Google put out on the TTS product was maybe last March, and that is now that plus a bunch of improvements are what you saw in the Google Duplex demo. So that's actually been productized and put out there in under a year, which is sort of stunning for the fact that that was actually just basic research into this and then translated immediately into industry. So one nice thing about deep speech also is that it has this 0.3x MacBook GPU scaling factors. What that means basically is that if you're trying to use the deep speech project to do ASR, you're able to do it at 0.3 real time if you're using a normal MacBook GPU. Of course, you can put it on something much bigger, much heavier, and go faster, but it does mean that you can actually do this ASR using this open source project in real time. It is a bit complex to get set up. It's very fun to get into, and I recommend going to the deep speech GitHub repo and looking into it. There's a lot of information there on that one. Next up, so now you have your speech, you've taken it, you've converted it into text. Terrific. Well, what are we going to do with it? You can translate it, you can do a number of things. One thing you can do is do some NLU on it, right? Some natural language understanding. And there was a talk I gave at AstroCon back in the fall that has a lot more of the actual math and machine learning models behind how this stuff works. So if you're interested, go check out a talk I did back then. So I'm not going to get too deep into how word vectors work and how all the linear algebra can work. But suffice to say, Raza is an open source project that puts together a number of different NLU tools, Spacey, and a couple other ones, that allow you to do stuff like throw in a question here, like I want something delicious, and it'll pump out what your intents might be. Let's say we're doing this common project is doing a restaurant search right here. So what we're doing is I want something delicious. It knows that you're looking for something, right? Your intent ranking and the confidence about 45% is you're trying to do a restaurant search, right? Confidence about 32% is you're saying yes. 11% is goodbye, and only like, what is that, 9% is you're trying to greet it. So it knows basically on the confidence rankings there that you're looking for a restaurant, because you say, I want something delicious. It knows you're looking for food. The model's been trained that way with this sort of corpus over here. It knows restaurant search. These are the words it's supposed to try to look at and figure out, like, this is what you're trying to search for restaurants. So the important part there to realize is that this is something you can actually just run. This is a Docker container you can download. Raza has a Docker container. You can go to Hub right now, download it, train it on any kind of NLU model you want. And this will do things like replace a number of different online services like Luis.ai or Wit.ai, some Dialogflow style interactions here, where you can actually just do all of your own NLU. And I suggest going to look at this as well. It's a great project, and it's incredibly fast to stand up, and it runs very, very quickly. So now we have ASR, we've got the NLU part of it, which is pretty exciting. So now we got to figure out, we want to go back to speech. And this is where things this is one of the things that I'm kind of the most excited about, because it's happened so fast. The project at Google is called Tron. I don't know why they called it that, but it's fun to say, and the graphics they use are cute. And so what they did they published this last March in 2017. They continued to iterate on it. They finally published Tron 2 around December of last year, and they finally came out with their prosody settings, which is intonation, inflection, all those sort of improvements to how we talk. So, if I talk like this, it's fine, but then if I talk like this, it's the same voice, but I'm just using different modulations, that can all be encoded now, and actually from a trained speaker's voice, you can then modify those and get entirely different kinds of voices. And like I said, this is what they're using in Google Duplex, most likely, plus some other stuff. They actually came out with another research paper as of, I think, a couple weeks ago that does some even more advanced learning of voices and then creating new voices from those learned voices that just sound like brand new people. It's very impressive. I have some examples here. Let's see if they actually play. Nope. Is it possible to get audio at all? Oh, here, hold on. The mic's turned down. Okay, here, one sec. Well, I don't want to mess up the audio on this whole thing. I can't hear it out of the laptop at all either. Here, one sec. We'll just go this. I'm going to undo what you did here for a second, Dan, because... What? No, let's try this.
No, you don't need that one.
The output volume. The output volume's all the way up. Output? Yeah. Yeah, nothing. That's right. There's a streaming thing happening. It's okay. Come find me afterwards. I will play these for you. But they are very, very cool. And this would be you'd be very impressed right now if you're listening to them. It is something along the lines of, there's a woman's voice being like, the flight to Los Angeles to New Orleans leaves at 5:30. And then the same exact trained model, the voice goes like, the flight to Los Angeles to New Orleans leaves at 5:30. And it's like, what? This is the same trained model. It sounds like a real live person. It is incredibly, the fidelity is incredibly high, and it's very cool to listen to. I'm just going to skip through a bunch of these. There we go. All right. So there are also cloud services, right? We all know that. Uh-oh. I broke it. Hold on. There we go. All right. There are cloud services that implement a lot of this, right? That we can pay for this these days. Tron is something that you can run yourself as well. There are containerized implementations of it, but it is probably one of the harder ones to get up and going. The models that are trained on it are not nearly as good as somebody like Google's model. The examples they give in their papers are also pretty fantastic, but obviously we're based on a lot of data and a lot of crunching and number crunching. So there is some limitations to the fact that we just don't have the power and we don't have the trained data sets that these large corporations do. It's one of the biggest problems with machine learning right now, right? Probably the biggest important thing to get in any kind of machine learning application or AI application is a nice, clean data set. You need good data, you need it well structured and well parsed, and that's hard to grab. It's not impossible to grab, and there are things that are letting all of us do it. Mozilla actually has a a project out there that is letting everyone contribute their voice. We all read the same audio samples. They're trying to get this going to so we have this giant corpus of data that we can all use for everything. And it's a little bit slower. One nice thing is that the algorithms are being public. So one nice part is that we know all of the math, we all know how they're doing it, just need to be able to get the data and replicate it ourselves. So this is now not working. Why doesn't it stream when I go forward now? I'm just going to keep doing this one at a time. All right. So that's old school. What's next? I'm just going to keep going like this for a minute. Beep, 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 boop. There we go. So let's move on a little bit more to some kind of newer advancements and something outside that classic stack of ASR, TTS, and NLU. So this is kind of an interesting project. This one's called RAISR. This is another Google research project, and what it does is basically it's sort of a form of super resolution upsampling. So we all know about upsampling, right? You just take a low-res image, you can upsample it using bicubic or linear sort of upsampling to get a higher res image. Well, that's pretty cool, except for the fact that it usually comes up kind of like blurry and it's just not that exciting. Like you upsample it, you're like, oh, it's an upsampled image, all right, whatever. This machine learning project uses effectively low-res, high-res image pairs, or even more appropriately, low-res, a cheap upsampled, and then a high-res. It's kind of a three-step process to actually do a super sampling of the high-resolution image. And what I mean by that is, what it does is it goes through and does edge detection. So it does a low-res image, it upsamples it, so it has kind of the blurriness, whatever. It also has the high-res image over here. It learns which filters it can use to basically, on a sort of pixel range, figure out which filters apply the most appropriately to any given part of the image, and then can apply those filters later. It basically learns how to create the most appropriate high-res image based on simple upscaling techniques. And it's pretty great. So what it can do is take stuff like a little picture of our esteemed leader, and then kind of upsample, and it's kind of noisy and grainy and blurry, and using some of that edge detection and kind of compensation for noise, it can generate a really clean upsampled image. Why is it exciting for us? Well, one thing is that it runs 10 to 100 times faster than traditional super scaling, upscaling techniques, which is pretty great. Something we really need. It is fast enough for real time. It was designed to do that. And what does this mean for us as an industry? Well, imagine we only had to send 25% of the data, right? Imagine we're trying to send an actual large 4K or 1080p stream. What if we only had to send 25% of that, and the client side can then super scale that and get the resolution on that we need? That's a great bandwidth savings cost, right? This is something that we could really use today. This would be great for mobile. Sure, we're offloading some of the processing to the client side, but depending on what it is and the application it is, you could really, and if you're bandwidth sensitive, this could really make a big difference. So that's kind of an exciting thing. I think stuff like this is going to be utilized super heavily. This came out a couple of years ago or a year and a half ago, but there are, I think, C libraries for this if you wanted to go implement it today. There's Dan. Love him. Another project that's out there is called RRNoise. So this one basically is learned noise suppression, right? Did it not go? I don't know why it won't transfer slides. You, Apple, give me a new laptop. There we go. So RRNoise is a Mozilla project, and it kind of combines classical digital signal processing algorithms that kind of scrub noise and mixes it up with some recurrent neural networks. And what they figured out was by doing that, on a per band basis, what they could do is this is the original, you can kind of see an original spectrogram down here of what their stuff looked like. And this is kind of the cleaned up one. And you can see that this is the audio sections right here. These were just kind of noiseless gaps in here that they wanted to get rid of. It's pretty noisy over here. This is not super great. And cleaning that up with traditional processing, leaves a lot of noise and leaves a lot to be desired in terms of attenuating signals. A lot of this uses low pass filters to do kind of averaging across. And so what they did with RRNoise was they wanted a real-time solution that could be used particularly in VoIP and WebRTC calls. They knew the signal-to-noise ratio on a standard WebRTC call is about 20 decibels, which is actually pretty good because of a lot of the work that Google and people have put into a lot of the noise suppression stuff already. And what they want to do is be able to run this and be able to reduce background street noise and background car noise as you're driving along kind of anywhere. And again, if you could hear the noise from my laptop, you would hear they have generated some samples. And what they can do is actually actively reduce all noise. They've trained it on about 3 or 4 hours of people speaking and about 5 hours of generated noise. And they can actively remove background car noise, street noise, and you can kind of hear it a little bit in the person's voice when they're talking. But what's interesting is that they pointed out in this project that people are very, very good at picking out the human voice in the background, right? You might not think like, well, I can still hear the person. There's a lot of like background noise. I can still hear them. But it's very fatiguing. One of the problems with long conference calls, things like that, is that you just get tired. A lot of background noise. Your brain is making a lot more effort to pick out the human voices, and it is a much better psychological effect to have all of that noise removed as much as possible. It provides for a much cleaner experience, and people are just generically happier about it. And so it's one of these things that people might not even know they want until they get it, and then once that goes away, they're like, why is this so much worse than it was? And so again, this is great. This one is designed to just very minimal look ahead. It only uses 10 milliseconds versus if you're trying to do more advanced noise reduction stuff and you have the entire audio sample, you can do a lot more scanning through it. Again, we don't have that. We only have, we have things as they're coming along. We don't have the ability to do anything look ahead. I think the last thing down there is wrong, but it does. So ignore this part because that was a copy from the previous slide. But it does run about 60% times faster than real time. So you can really do this very, very quickly. It can run on mobile. It was designed to do that. Again, it's an open source project, so you can kind of go and just take it over. So then what else can we do, right? So those are actual projects you can go right now, download, and incorporate. A lot of them have C libraries or Python libraries. You can play with them today. This one's a little bit more speculative in the sense that nothing is out there that I'm aware of, but it's kind of a cool idea. There are ideas that we can improve network performance using some machine learning models as well, right? So we have a lot of data at our fingertips all the time about our calls, right? We get things like, we have just all kinds of information about what's happening in the network, what's going on with the calls themselves. We have RTCP, we have any kind of latency checks, people are doing bandwidth stuff all the time. And traditionally they just use one or two of these ideas to try to change the bitrate of the stream. I think Lital was saying at the Messenger talk yesterday that's what they do, right? They're doing constant bandwidth estimation to try to modify the bit rates to make sure they have a good client experience. Well, what if you could just do more than that? What if it was more than just modifying the bitrate based on latency? What if it also included things like who is actually talking? What if we decrease the bitrate of streams of people who aren't talking or who haven't moved in 5 or 6 seconds, and we increase the one of the active speaker, right? Sort of dynamically in real time. It's kind of everything's shifting up and down constantly. The idea that we're just constantly, that maybe ramping up and down bit streams is too simplistic. Let's think more, we're operating in real time. We can just change things all the time to optimize it for any kind of given conversation. We can toggle all kinds of things, buffers, even the kind of codec that's being used can be reinvited halfway through. I mean, that is very unlikely, but who knows down the line. And then after the call, we can do things like look at the metrics of the call, figure out what happened during it, right? We can figure out if there was an issue with the actual routing. Let's say the call gets a very low rating. We look at a lot of data afterwards, and the model starts to learn the idea that, well, if somebody's connecting from Helsinki and somebody's connecting from San Francisco, it's optimally using this path, but there's something screwy in that path. This is just not going well, versus a couple randomized ones that are going down through, New York and then back out through Dusseldorf or somewhere. It will learn the network better than you think it could, and better than the questions that you would give it and ask it and notice, be like, why is this link flapping or why is this having a problem? We can just go and sort of understand that. And you can use sort of unsupervised learning methods to detect those kind of things. You can also use unsupervised methods to do things like you can pick it up, you sort of get your data out there. And one nice thing about all this data from our calls is it's all very standardized, right? We have all the CDRs and all the call data. It's very same across all the different platforms, so you can actually have a very large data set very quickly. And then it's just a matter of getting in there and learning how to do some of the machine learning models in TensorFlow or PyTorch or whatever you want to use, and asking the right question, which is sort of outside of the scope of this. Oh, look, now it's gone. Cool. So interestingly enough, VP9 actually includes some machine learning in it. I don't know if most people know this, but there was a guy named, I think it was Yang Xian, I'll be getting that backwards, but he put out he went into VP9 as an intern and said, our encoding is slower. AV1 is kicking our butts. How do we speed up the encoding process of VP9? And VP9 does something along the lines of it uses 64 by 64 super blocks inside the video frames, and what it does is it can break those down to 4 by 4s, and it does sort of a recursive shrinking to make sure they can find the right partition size that minimizes the cost function of encoding time and quality. And it will just keep going down, 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 down. And I think it might even just do it originally just did all of them until it found the best cost and then would use that one. It's very slow. It's a very slow process because it can go from 64 to 64 down to 4 by 4. So he thought, well, can we speed this up? Can we train a model based on existing like 4K video that says, okay, at some point, this is probably going to be your best cost function. You're already there, so stop the encoding check down the partition size and just use this one. And it turns out he was right. So he got that all trained up and whatever else. And he was able to increase the encoding performance of the existing VP9 encoder by about 25% on 4K video and about 10 to 15% on standard like HD video, which is kind of an amazing improvement, right? And the code, if you follow this link later, I'll put this online, go to that GitHub repo. This is the actual commit in VP9. It's not that much. Like the actual lines of code that are in there are maybe 100, maybe 75. For 25% improvement, it's kind of astounding. So I give a lot of credit to him for sort of noticing that was there. And that is a good example of someone seeing a problem where they're doing a research like that, sort of a recursive search, and knowing that, hey, we're looking for some sort of like cost function. And that's the basis of a lot of these machine learning algorithms, right, is the fact that you're trying to find something at the end that is an optimal solution, and you have data before that you can then generalize for that specific use case. So it was smart of him to see that. Something we could then, using that idea, you can also do sort of more future ranging things like imagine, let's go back to the imaginary video I had, sending that to people. You could do something like use selective areas of encoding, right? What if we can encode the frames of video, the background of it, like if we could do sort of feature extractions from standing up here, you see my face, my body, I'm moving my hands around, a lot of motion, but this stuff's never changing. Who cares about this stuff back here? In fact, my slides barely change as it is anyway. So like you could just kind of statically put that on there, basically encode that once, tell the far end that that's always the same, and never send this part of the picture again, and just highly encode me and send me at a much higher rate, and just save all that processing power, right? Again, you're saving processing power, you're saving decoding power, and this requires a lot more thought about how we're transmitting video and how we're transmitting information to the far end. Again, this is something I was talking about the other day with some people here as well. And that's what's been sort of great at this conference, is I had a lot of time to sit around with people at dinners and talk about, different ideas sort of in this field as it moves forward. What if, again, like if most video conversations that we have or audio conversations are a bit ephemeral. People they don't need really high fidelity. They don't need to be saved and archived. I'm trying to get some information across. This is not like critical information. So why do we have to pump, 1080p video or like 6 streams of that to a conference where half the people are sitting at home and haven't showered? Why are we like spending all this bandwidth to do that? What if we could decrease that or fake it in some ways, right? What if we could almost recreate, do that sort of that upsampling thing on me on the far end and just reduce the overall costs to the system, because it doesn't really matter. If my background, like let's just say like we just send, I'm sitting at home in a chair and behind me is, just random my house. And if they know that my house very rarely changes, and so that's just always kind of the same background image with some subtle variations. Maybe that's then sent as like a pre-rendered image to everybody, and that just really never gets updated. It doesn't really matter. Or if we're doing something more advanced like AR or VR transmission of video, what if one person is just sort of like, there's going to be weird situations where maybe if I'm standing next to somebody over here, they're being generated in real time, but also like just in a worse quality or kind of half being faked, like maybe they raise their arm or the fake gestures are being like, sort of animated. And these are the kind of things where it doesn't really matter because no one's really paying attention to those small subtle details, as long as we're getting the important parts like our faces and things like that correct. Again, this also works for voice, right? The voice part of it is, what if we don't transmit actual voice? What if using some of the more advanced, and again, if the audio were working, I would let you hear this, the copies of people's voices, right? There's some companies out there that are actually duplicating people's voices, but 2 hours of speech can give you a pretty good replica of someone's voice. That's the paper that Google actually just put out this month, was doing that again, was an even more advanced version of like just hearing someone talk who's not actually there. So what if in the future we just send text accent voice pairs around, or triplets, and your voice is just regenerated on the far end, right? What if it's not actually you talking, but it's like 95% of what you would say and how you would say it, and who really cares, right? We're not transmitting anything. It's like what I say, half of what I say doesn't matter anyway, so this might as well just be text that you're just generating on the fly. They can have me say whatever you want. All kinds of, I could swear at lamps all day long. So here's the best part, though, is that a lot of this gets down to the idea that there are also a lot of nefarious things to do with this kind of stuff. So this is very cool. I can think of lots of ways this will help society and benefit all kinds of people. But there's also kinds of crazy things you can do. Now that you're able to copy people's voices, this is going to be a real problem, right? There's some examples in here I was going to give too. We all talk a lot. We've all been at conferences for a while. There's many hours of us recorded. I know Lorenzo's probably got like, a good solid 15 hours of you I could copy somewhere. And so generating those voices is not complicated. I attempted to do it last October with Matt Jordan from Digium. I didn't have it. Turns out the GPU power required to actually do that at the time was a little bit too much, and I didn't want to spend the money. I'm sorry, Matt. But it is possible to extract the audio from a close feed like these mics and then regenerate our voices. And what can you do with that? And this is something else cool that I was going to show here as well if the audio were working. They have one where the guy is speaking in Mandarin, and what they've actually done is take his voice and his accent and intonation and then make him speak English. So it's like if he had learned English and was sort of speaking it haltingly, and it sounds like the same person, just talking in English in his original Chinese capture. It's really sort of incredible what they can do. Let's just power through. There's like 6 audio files here. There we go. You guys might have heard deepfakes, right? This was big in the porn industry for a little while until it all got banned. But it's not just that too, right? This is, maybe this will actually play for a minute. Damn it, hold on. This is a good one. This will actually work because this is a video one. Let's see here. Come on. You can't hear him. You can't hear him. He's talking to Jean-Luc Picard and Kevin Spacey. Yeah. Right? Is that not Kevin Spacey? It kind of looks like Patrick Stewart, right? Here, he'll come back again. There he is, right? Tell me that's not Kevin Spacey. And then here, okay, let's see. I'm sorry, Nick Cage. It's Nick Cage. Look, and here comes Nick Cage again. Is that not Nick Cage singing? First I was afraid, I was petrified, right? Here he goes. Yeah, right? So that is, the deepfake stuff is basically exactly that, right? What they've done is they have so much captured imagery of these celebrities, they can map their faces onto sort of arbitrary bodies. And the closer you are looking to them physically, and it's much easier. And it is bad a lot of the way. There are a lot of very bad implementations of this. But it's also some pretty amazing ones like those, where if I wasn't paying attention, I'd be like, wow, I didn't realize that they'd replaced Patrick Stewart with Nick Cage. That's pretty great. And this is going to happen in all kinds of industries, right? Imagine you could do this with, and some examples I didn't show, and the ones they always show in the news that you might have seen are like, what if you could fake, Donald Trump or Barack Obama saying things, right? You could fake politicians saying outrageous things. Not that you have to fake it these days, but you could. Or you could fake anything. You could fake my mother calling me on a video chat, right? And then the copies her voice. So that gets into the idea of like, there's identity theft. You could do something like copy an actual person, have them call up a bank, have them call like loved ones, say, I need you to come like visit me at the hospital or something horrific like that, and then go in and rob their house. It's a very mild example, but this is some real things. I was at a conversation in LA that I went to with my wife, who's a journalist, and she got invited, and I kind of tagged along, and it was with the ex-head of DARPA and a few other people, and they were talking about a lot of these sort of concepts of what the military is trying to do to combat this stuff, to detect it. There was a lot of idea about how do you trace the authenticity of these images, and that's something as an industry we should be looking into perhaps, is trying to verify authenticity of these things before they're created, or logging when it was created so we can kind of backtrace it. I raised my hand at one point, and I was like, we are working on this actively. We are copying people's voices. This is happening. Even if we stop doing it in the U.S., it's going to happen all over the world. So this is coming. What should we do? And of course, they had lots of answers. And in Hollywood, this being Hollywood, I said, we're also going to put voiceover actors out of work. And I'm sorry Allison isn't here. I keep apologizing to her. She's safe, but the next Allison is never going to have a career. And so I'm talking to the person. I say, putting these voiceover actors out of work. I get into an elevator to go downstairs for after the conference, and I hear from behind me, somebody just go, "Hey, buddy, don't take my job." I turn around, and it's James Vanderbeek, who is standing behind me, and he says, "Voiceover gigs are the best part of my career, like best part of my job. Stop trying to take away you're a job killer. You're killing my jobs." And I'm like, "I'm sorry, James." And he'd been there, and his point was that, he's fine. All the celebrities these days are fine, but going forward, that's something to think about. If someone has a career in voiceover, and somebody unscrupulous gets them into a booth for 60 minutes, 2 hours, that person could then become the voice of Chevy for the next 15 years, and they kind of would own that if they signed the wrong legal documents. So societal problems here we have to think about too, like protecting people, showing that this stuff is possible, so they know what their rights are, they know what they're getting into, and it doesn't just surprise them. Again, my wife thought the idea of package theft was a good one, right? If somebody comes up, they can like fake your camera out and be able to get into your house somehow. and psychological manipulation. Anyway, that would take a little bit longer if the audio had played. Come find me. They're exciting. You can find all the audio online if you Google different projects as well. I'm Evan McGee. I'm at SignalWire. This is my Twitter and my everything else. So thanks so much.
That was brilliant and disturbing. So, a couple of questions maybe? Anybody got a question for Evan? Or are you all too worried about your futures?
Question is, where's the coffee, right?
So, in the audio world,
Yeah.
someone speaking in a microphone is going speech to text, NLU, and then return back into voice somewhere. Does the characteristics like assertiveness make it all the way through that chain?
Could you say it again into the mic? I can't
Do
hear.
characteristics like assertiveness make it all the way through that chain?
Yes, so you can optimize the models to search for exactly that kind of thing, right? If you're looking for something, you would have to do some extraction on the ASR layer, right? So the ASR layer would have to somehow encode the idea that you're looking for the concept of assertiveness or positivity, right? You can pull some of that out of the actual text, right? There is emotion and sentiment analysis that's pretty standard and straightforward. And on video, there's like smile detection is how when like Facebook does or whatever, when you smile and a rainbow vomits out of you. So you'd need to then train your model to know that you're looking for that specific kind of assertiveness, and you'd have to supply it with what you mean by assertiveness, right? You'd have to train it in an idea that like, this is what assertiveness sounds like. I don't know of any existing data set that has that, but certainly you could build that yourself and say, this is what we're looking for, and call this assertiveness, and then somehow put that into a word vector or some sort of representation in text. And then generating again with the Tron TTS stuff would be very simple. So the hard part in that one is actually just getting the ASR to understand that concept. But then from the actual text to speech is actually pretty straightforward. Mm-hmm.
Just a quick question about the deep speech part. So
Yeah.
I remember watching a presentation they made at the last FOSDEM and explaining how, at least when they presented that they were still working on kind of different chunks of text and so on, and that they were planning on working on streaming and so on.
Yeah.
So at the moment, the usage of chunks themselves pretty much enforces the context that you are trying to extract from something. So what do you think the challenges will be when you will be able to actually work on a stream of audio rather than different chunks of text in order to allow them to figure out that this is part of a sentence and not part of another sentence or something like this?
That tokenization side of it. I think it's a combination of things, right? I think the deep speech guys are focusing more on, like you were saying, like chunks of text. I don't think that the models they're building, Baidu has since released 2 more research papers on the deep speech technology, Deep Speech 2 and 3. They're still focused primarily in this project on Deep Speech 1 and 2 a little bit, including some optimizations for just lowering the word error rate. They're focusing mostly on lowering word error rates. So for long form, free form text like you're talking about, it might require a more advanced concept or a different kind of model than what they're doing. I'm not sure that what they have will necessarily be extensible to like a long free form sentence declaration. That being said, you could do it with that, right? You can chunkify the audio yourself in real time and kind of like break it up and figure out where the sentence breaks are just based on other parameters. You could train a model that could understand when the break of a sentence is, just based on different, you could train it on VAD or some example of like how RRNoise does like, detection of different audio parameters. So you have to figure that one out. Or you could just have it go, the whole way along, just have it go. And then as the text comes through, feed that into like some sort of text classification system, like a spacey, that it understands the way human speech works and can then break that up for you. I think that's the way a lot of people are going, which is that they'll just like stream, the text will go, they'll go. If you were over at Mike Jarris's talk right now, he was demoing Dialogflow, Google's product, and you'll see that as you're talking, what they do is, and we actually show this on the SignalWire website, that like as you're speaking, you get back the real-time feed, right? And the audio, the entire like sentence changes as you're talking. So if you say, "I'd like to go to a restaurant tonight," you see "I'd" and then IDE and then like, and then it gets all weird and funky. And Google actually sends you revisions to the entire sentence structure as you're going along, and then it just checks the silence at the end, and that's when it breaks the sentence up. So even they don't do like real long-form streaming text analysis yet, or speech analysis, because it's just too complex. Yeah.
Great. So thank you very much for that. Big round of applause for Evan, please. And now we've got a 5-minute break for you to dash out there and grab a coffee and come back in 5 minutes for a talk on how to build Skype in an afternoon or not. Thank you very much.